Hey everyone, Dr. Robin Bond here. Welcome to the Visual Chemistry series. This week's videos are called Chemical Recipes, and they're designed to teach you about balancing equations. So, our first installment, we're going to understand why I use the metaphor of recipes for balancing equations by talking about two different food analogies. We're going to talk about notation, and then I will lead you into balancing your first equation. So in the first one, we're going to talk about what happens when you make pancakes. Imagine making pancakes. You might start with flour, eggs, milk, and a few other ingredients. And if you used this many ingredients, you'd expect that you would get more than just one little weensy pancake, right? Likewise, if you only used part of an egg and a little bit of milk and a couple tablespoons of flour, you wouldn't expect to get a whole huge plate of pancakes. Now, if you used just a few ingredients, you might get a weensy pancake, right? And if you used a whole bowl of ingredients, then you would expect to get a lot more pancakes. What the pancakes teach us is this idea that we call conservation. Essentially, you don't get more out than you put in, or you also don't get less out than you put in. Whatever you start with is pretty much what you finish with. So it might change slightly in terms of form or what it looks like, but the basic ingredients are all still there in some fashion. And that is the number one principle that you need to understand in terms of balancing equations. Now the second one, we're also, hello cat, this is my cat. The second one is also a food analogy, as I said, and we're going to talk about chemical packages, which is what I call molecules. So, you know food comes in packages. Here's a package of cheese, and you can also buy bread in packages. We don't normally think of it as a package, we call it a loaf of bread, but the fact is you get bread in loaves, not in single slices. I want you to think about this in terms of making sandwiches. So let's imagine that you're making sandwiches, and you're not just making one sandwich for yourself, you're making a whole bunch. And you don't have to make a specific number because you're not quite sure how many people are going to come. Let's say you're making this for a group event, but what you do need is you need to not have any leftovers. So whatever sizes your stuff comes in, you have to use that all up. So I'm going to say, for purposes of this metaphor, that you're making cheese sandwiches, and so you are just going to use 2 slices of bread in every sandwich, and you're going to use 1 slice of cheese in every sandwich. So each loaf of bread has 20 slices, and then your cheese, each package has 12 slices. And so let's see what happens as we start to make sandwiches. We take our 20 slices of bread and we start putting them out for sandwiches. So we're going to do 2 slices of bread and 1 slice of cheese, 2 more slices of bread and 1 slice of cheese, and then we're going to keep going. And so now we've used up all 20 slices of our bread, and we still have 2 more slices of cheese. What are we going to do? We can't just go back to the store and say, hey, can you give me 4 more slices of bread? That's not how they sell bread. They sell bread as loaves, right? You can't buy part of a loaf. You have to buy a whole loaf. So let's think about this differently. Let's think about what would happen if we had a whole bunch of loaves of bread and a whole bunch of loaves of cheese, and we just started putting them out and seeing where both of those packages, both the loaf of bread and a package of cheese, run out at exactly the same time. Okay, so here are 20 slices of bread, and we're going to put down our 12 slices of cheese. And what I'm going to do here is I'm going to mark off where these packages end, right? There's 1 loaf of bread, 1 package of cheese. So you can see we need more bread, so let's put down another loaf of bread. And now we have enough bread for all that cheese, but of course, we need more cheese to finish off the bread. So let's add another 12 pieces of cheese. Well, now we have cheese for all the bread, but we don't have bread for all the cheese again. So we're going to need another loaf of bread. And now we have bread for all the cheese, but still, once again, we need more cheese to go with our bread. And you can see what's going to happen here. We're going to have to keep adding another package of bread, and another package of cheese, another loaf of bread, another package of cheese, and another loaf of bread, and look! We did it! So what did we end up with? 1, 2, 3, 4, 5 slices of cheese, and 1, 2, 3, 4, 5, 6 loaves of bread. So I've used 2 food analogies. Let's think about what these analogies are telling us. First of all, the pancakes told us that we end with the same amount of stuff that we started with. In other words, stuff doesn't disappear. It doesn't magically appear either. We have to have the same amount of stuff that we started with. That stuff may change what it looks like as we go through our reaction, or in this case, the cooking of the pancakes, but it's still pretty much the same amount of stuff. The second thing that we learn from this is that everything comes in packages, and you can't buy part of a package. You have to get the package that things come in. And so the last thing that I'm going to say is that when we're talking about chemistry, we have to use full packages of everything, and we have to end up with a full package of everything. In that last example, our package was a sandwich, right? But we couldn't have, a half sandwich or whatever. We had to make full sandwiches. Now, that's not true in real life when you're cooking, right? You can only use part of a bag of flour, etc. But when it comes to chemistry, we have to use full packages. So, chemistry, packages. What do packages look like in chemistry? The answer is they look like molecules. As an example, let's look at a package of hydrogen gas. Hydrogen is element 1 on the periodic table, and you can see that in addition to the full name, there is a symbol, H, and so we're going to use that to delineate what our package looks like. So hydrogen atoms actually don't come by themselves. The way we find them in nature is 2 hydrogen atoms stuck together, and we write this as H2. And the reason we use this symbology to represent this package is we have our element symbol, so it's telling us this package is made of hydrogen, and the 2 tells us the number of atoms of that element. So we have 2 atoms of hydrogen. Let's look at another package, and here I'm going to show you something that has hydrogen, but also oxygen, and this is something you probably know because it's in your house. This is hydrogen peroxide, which we write as H2O2. So I've shown you what a package looks like. And this is how we write it. We say it has 2 atoms of hydrogen. Again, we have H for hydrogen and 2 to say that we have 2 of those atoms. And we have O2, 2 atoms of oxygen. Okay, so H2O2. That's a package of hydrogen peroxide. One more. We're going to use sulfur this time and oxygen, and we're going to make sulphur trioxide, which is something you'll see in another video. So here we have 1 atom of sulfur, and you'll notice something here, and this is why I showed you this one. We only have 1 atom, but there's no subscript that says 1. So if you just see the element symbol and you don't see any number, that tells you you have 1 of that thing. And then we have 3 atoms of oxygen. So now let's take this idea of chemical packages, also called molecules, and let's use it to start balancing an equation and see what chemical recipes are all about. What I'm going to show you here is a way to use visual aids to look at these chemical recipes that we call balanced chemical equations. And what I'm going to use, I just have some of these glass beads that I picked up at Dollar Tree. And you can use pretty much anything in your house that you have lots of. But for this video, I like having the different colors and the small sizes. You could also use Legos or marbles or pretty much anything, like I said, that you have lots of many different types. So here's what that package of hydrogen looks like with the glass beads. Each green bead represents one hydrogen atom, and I've drawn a circle around it to indicate that that is one package or molecule. And now let's look at sulfur trioxide. The package that is sulfur trioxide has two different types of elements. And so you can see this one right here, if you look at your periodic table, S stands for sulfur. And then this element right here is oxygen. So what does this tell us about our molecule, our chemical package? It has one sulfur, and we have 3 oxygen atoms in that package. So 1 sulfur, 3 oxygens. So what happens if you have more than one of these molecules, of these chemical packages? Let's say we have 2 hydrogens. Well, you can see that each of these packages has 2 hydrogen atoms in it. We don't call that 4 hydrogens. These are separate packages. That's like going to the store and buying 2 loaves of bread. You don't say that's a loaf of 2 bread, you say that's 2 loaves of bread. And in fact, that's what we do with chemicals too. So with molecules, we say there are 2 of these molecules that have 2 hydrogens in them. 2 different packages. So before we start, I'm going to show you one more thing, which is how we write chemical reactions, how we write what's happening in this process. So we have reactants, and you could have 1 reactant, or you could have 2 or 3 or 4 reactants. Sometimes people call these reagents. But what those really are the ingredients for our chemical recipe. We also have products. And that's pretty much what it sounds like. That's what you end up with. So we're going to put all of our ingredients or reactants on this side of the reaction, and we're going to put an arrow, and this arrow symbolizes the chemical reaction that happens, that turns these reactants into the products. So you could think of this even with cooking, right? Your reactants are milk, flour, eggs. Chemical reaction turns it into pancakes. So with that said, let's look at a chemical reaction. So what we're going to look at here is a very simple reaction. One in which hydrogen gas, H2, so remember this is something where you have 2 atoms of hydrogen in 1 molecule, or you could say it's a package of 2 hydrogen atoms, plus oxygen gas. Again, this is O2, so we have 2 atoms of oxygen in 1 molecule of oxygen gas. And that's going to make water, which is H2O. And again, that means a package that has 2 hydrogen atoms and 1 oxygen atom all in 1 molecule. So I'm going to put a line right here to remind us that everything on this side is reactants, or you could think of them as ingredients, and everything on that side is products, the thing that comes out of this recipe. Now, let's see what happens if we try and take these ingredients and put them into water. So in water, we have 2 hydrogens, which we can get from our package of hydrogens over here, and we also have 1 oxygen, which we can get from here. And you can see that we have made 1 molecule of water, but we haven't used up all our ingredients. And if you'll remember, that is something that has to happen in every reaction. You have to use up every single ingredient. So what are we going to do with this oxygen? Well, we could use it to make another water, right? Because every water molecule has 1 oxygen. Well, it also needs 2 hydrogens. We don't have 2 hydrogens. Could we have started with 2 hydrogens? Yeah, we could have started with 2 molecules of hydrogen, 2 packages of hydrogen, you could say, and then we would have enough. So what we have here is we have 2 molecules of water. What did that come from? It came from 1 molecule of oxygen and 2 molecules of hydrogen. So this is what we call a balanced reaction, one in which all of our reactants or ingredients get used up to form complete molecules or packages of our products. And once again, you can see we have 2 molecules of hydrogen and 1 molecule of oxygen. If there's no number in front of the oxygen, then we just assume it's 1. And then that makes 2 molecules of water. So that is the idea behind balancing equations, when all of your reactant molecules get used up to form complete product molecules. Well, that's it, guys. I hope you found that useful. I hope you now understand why we balance equations and the notation that we use, and also the basic principles behind how we balance equations. And in my next video, we're going to get more practice in using manipulatives to balance equations. I'm not only going to break out the glass beads, I'm also going to show you how to balance equations when you don't have glass beads or any other sorts of things around. And in fact, which is in fact the way that a lot of students balance equations. See you next time.